Hi, I am Dr. Harikrishna Mulam, Associate Professor, Department of EIE, VNR VIGNANA JYOTHI. Today, we will see one more problem related to time response analysis. This is the problem, and if you see here, a unity feedback system. Therefore, based upon that point, we can write the feedback transfer function h of s is equal to 1. Has a open loop transfer function g of s is equal to 10 by s into s plus 2. Therefore, open loop transfer function of the system is equal to 10 by s into s plus 2. Now, we need to find a rise time, that is TR, and percentage overshoot, that is percentage MP, peak time, that is TP, and settling time, that is TS. These four parameters together, we call it as time domain specifications. When the input is step input of 12 units. So far in the previous problems, we got unit step input. Therefore, the input R of t, we use it to write unit step input. It is mathematically written as 1. Whereas here, step input is of magnitude 12 units. Therefore, R of t is equal to 12. Okay. Here, we need to tell one important point. Actually, the formulas for rise time, peak time, settling time, overshoot are derived by considering unit step input. But if you derive these time domain specifications for a step input of magnitude A, here in this problem it is 12, even then the formulas remains same. Therefore, the important point is the formula for time domain specifications remain same whether the input is unit step or step input of magnitude A. So the formulas will not change, okay? Whether the input is step input, unit step input, or step input of 12 units, 15 units, or in general, the step input of magnitude A. Then, so we already told several times, if at all you wanted to find these time domain specifications, you need to get the information about what is the value of undamped natural frequency omega n and the damping ratio zeta. If you know these two parameters, you can find all these time domain specifications using appropriate formulas. But if you want to find this zeta, damping ratio, and undamped natural frequency omega n, you need to first of all find out the closed loop transfer function of the system. Closed loop transfer function of the system. So, to find closed loop transfer function, the formula is given as the open loop transfer function g of s by 1 plus g of s h of s. Therefore, closed loop transfer function is equal to g of s is 10 by s into s plus 2 can be written as s square plus 2s whole divided by 1 plus g of s is 10 by s square plus 2s into h of s is unity feedback system. Therefore, if you simplify this expression, you will get closed loop transfer function as 10 by s square plus 2s plus 10. So this is the closed loop transfer function of the given system. But if you want to find zeta and omega n, you should compare this closed loop transfer function with the standard way of representing closed loop transfer function of a second order system. Therefore, you need to compare the transfer function with omega n square by s square plus 2 zeta omega ns plus omega n square. Always give preference to compare the denominator of the transfer function with the standard transfer function's denominator expression. So if you compare the denominator polynomial of the transfer function in the system with the denominator polynomial of standard way of representing transfer function of second order system, you can write this 10 is equal to omega n square. Therefore, omega n square is equal to 10. Therefore, you can find undamped natural frequency omega n, which is equal to square root of 10. The square root of 10 value is approximately 3.162 radians per second. Then compare this 2s with 2 zeta omega ns. Therefore, 2 zeta omega n is equal to 2. 2 gets cancelled. Therefore, we can write zeta omega n is equal to 1. And zeta is equal to 1 by omega n. Therefore, as omega n is 3.162, if you substitute here, you will get zeta as 0.316. The damping ratio of this system is 0.316. Its value is between 0 and 1. Therefore, this type of system is called as underdamped second order system. Anyway, we got the values for zeta and omega n. Omega n is 3.162 radians per second. Zeta is 0.316. Then let us find these time domain specifications. So the rise time is given by the formula pi minus theta by omega d, and we already know that this omega d is called as damped frequency of the system, which is given by omega n square root of 1 minus zeta square. Therefore, omega n value is 3.162 radians per second into square root of 1 minus zeta square is 0.316 whole square. If you find its value, it comes around 3 radians per second. It comes around 3 radians per second. Then the theta expression is equal to tan inverse square root of 1 minus zeta square by zeta. That is equal to tan inverse of square root of 1 minus zeta is 0.316 whole square. Zeta is 0.316 and its square divided by, once again, zeta is 0.316. And if you find its value, it comes around 1.249 radians. Actually, initially, while finding this theta value, tan inverse of this, you will get it in degrees, and you need to convert that degrees into radians by multiplying with pi by 180 degrees. So finally, your theta value will be 1.249 radians. Then rise time is equal to, once you get the values about damped frequency of the system, which is 3 radians per second, and theta value, which is 1.249 radians, you can find a rise time by using this formula, pi minus theta by omega d. Pi value is 3.14 roughly, minus theta value is 1.249 divided by omega d value is 3 radians per second. Therefore, if you compute this, it comes around 0.63 seconds. The rise time of the system is 0.63 seconds. It is the time taken by the response to reach 100% of the final value for the very first time. Let us find the remaining parameters also. That is, next parameter is peak time. Peak time is given by the formula pi by omega d. That is equal to pi by, we have already found this damped frequency of the system and we got it as 3 radians per second. Therefore, pi by 3, which comes around 1.047 seconds. Then settling time. We already told, generally we will compute settling time for an error of 2% steady state error or for an error of 5% steady state error. The settling time formula for 2% steady state error is given by 4 by zeta omega n, whereas for 5% steady state error it is 3 by zeta omega n. If you see previously here, we could show that zeta omega n value is equal to 1 in this calculation. Therefore, I can substitute that here. That is 4 by zeta omega n is equal to 1. Therefore, it is 4 seconds for 2% steady state error. Steady state error. And then for 5% steady state error, it is 3 by zeta omega n is 1, which is equal to 3 seconds is the settling time for 5% steady state error. Then finally, let us find the percentage overshoot in this system. We know that the formula for this percentage overshoot is e power minus pi zeta by square root of 1 minus zeta square into 100. That is equal to e power minus pi, zeta value is equal to 0.316 divided by square root of 1 minus 0.316 whole square into 100. If you find this expression's value, it comes around 35.12%. 35.12%. So if the overshoot, percentage overshoot is 35.12%, what is the peak overshoot? To find peak, this is the percentage overshoot, whereas peak overshoot can be obtained from this percentage overshoot, that is 35.12% of whatever is the input. So input is 12 units. Input is 12 units. So this percentage overshoot gives you information about the deviation from the desired value, okay, which is expressed as a percentage of desired value. Okay. Therefore, this peak overshoot is 35.12% of 12 units. That is equal to 35.12 percentage means by 100 into 12 units, which is equal to 4.2144 units. 4.2144 units. Therefore, let us see how the time response looks like. See, this is the unit step input, or okay, in this problem it is step input of magnitude 12, therefore 12 unit step input, and for step input the response of second order system looks like this. Okay, and this gives you information about rise time. Time taken by the response to reach 100% of the final value for the first time. That means at this point, at this time, it reaches 12 magnitude for the very first time. And we got it as, we got this rise time as 0.63 seconds. 0.63 seconds. Then this is the peak time. Peak time. Time taken by the response to reach peak value for the very first time. And here we could get this peak time as 1.047 seconds. And here in the steady state, we will come across this settling time. So settling time is this. Okay, and this settling time is equal to 4 seconds for 2% steady state error, and it is equal to 3 seconds if you go for more steady state error, that is 5% steady state error. And this percentage overshoot is this. From here to here, it is called as overshoot, which is going beyond this 12 units. So the input is step input of magnitude 12. Though it is, we are calling it as input, this input corresponds to the desired output. And from the desired output, the deviation is up to here. So this is the overshoot. This overshoot is expressed as a percentage of this final value or desired value. And we got it as 35.12%. Overshoot, peak overshoot percentage is 35.12%. But if you find that overshoot, we have found the overshoot, we got it as 4.2144 unit. So this peak value, okay, from here till this peak value, its magnitude is 4.2144 units. Okay. So this is about finding the time domain specifications of a given second order system. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.